Greeting guys! In this tutorial, we'll be fine-tuning Llama 3 on a dataset of patient-doctor conversation. We'll be creating a model tailored for medical dialogues. So we will learn to fine-tune Llama 3 on a medical dataset. We will also transform the model into a format which is ready for local use. What we will be seeing is we will learn about Llama 3 models and then fine-tune a Llama 3 model on a medical dataset, and then we'll be merging the adapter with the base model and push the full model to the HuggingFace hub, and then convert the model files into llama.cpp format, which is GGF format, and then we will be quantize the GGF format and push the file to the Hugging Face app. So fine-tuning large language models like LLMA 3, 8B for specialized tasks such as medical chatbots can be resource intensive. And we can use technique like LoRa and adapter, which is LoRa, and quantized LoRa, which is QLoRa, offers efficient alternatives, which enable the fine-tuning on consumer-grade hardware. So this tutorial, which provides a step-by-step guide to fine-tune Llama 3 8B using these methods. So let's dive in. Regarding Llama 3, Meta has released a new series of large language models called Llama 3, a collection of pre-trained and instruction-tuned text-to-text models. So Llama 3 is an auto-regressive language model that uses an optimized transformer architecture. So both pre-trained and instruction-tuned models come with 8B and 70B parameters with a context length of around 8K tokens. So Llama 3, which is 8B, is the most likely LLM on Hugging Face. So it's an instruction-tuned version is better than so Mixtral 7B instruct on various performance metrics. Meta have trained Llama 3 on a new mix of publicly available online data with a token count of around 15 trillion tokens. The 8B model has a knowledge cutoff of March 2023, while the 70B model has a cutoff of December 2023. The models use grouped query attention, which is GQA, which reduces the memory bandwidth and improve the efficiency. And the LLMA 3 model has been released under a custom commercial license. To access the model, you need to fill out the form with your name, affiliation, and email, and accept the terms and conditions. If you use different email addresses for different platforms like Kaggle and Hugging Face, you may need to fill out the form multiple times. Coming back to fine-tuning LLM, so we'll be using Kaggle as I said. So for this tutorial, we'll fine-tune the LLM chat model using the AI medical chatbot dataset from Hugging Face. So the dataset contains around 250K dialogues between a patient and a doctor. So we will use Kaggle notebook to access this model and free GPU as well. So let's see how we can set up our working environment. So before we launch the Kaggle notebook, fill out the meta download form with your Kaggle email address. Then go to Llama 3 model page on Kaggle and then accept the agreement. So this is the meta download form. So you have to fill this with the model that you want to have access and do submit your form. Okay, I will provide the link to this form in the description below. And then you have to go to Llama 3 page in Kaggle. So this is the page. So you have to accept and accept the agreement in order to access it. Okay. So sorry guys, I was trying to just do a tutorial fine-tune a Llama 3 8B model, but unfortunately I don't have access to this model. I've been waiting time, so I really would like to just showcase the demo using fine-tuning the TinyLlama, which is available locally from HuggingFace. So we'll be using this model to fine-tune with our custom medical dataset. Example, we have to launch the new notebook on Kaggle. So now we have to go to session and select the GPU option as an accelerator. So it's already just selected as GPU P100. And once we're done with it, we have to add the secrets we'll be using weight and bias to track our experiment, and also we will be need to add our Hugging Face token. To do that, let's go to add-ons secret. So from here, I have to add the key value first. So it's already added in my case. So initiate the Kaggle session by installing all the necessary Python packages. Okay. So basically this package, it just install the following packages like transformers and the dataset library, which is easily accessible and helps for sharing the dataset, and accelerate, which is for like optimizing the accelerating the model training, and then FEPT, which is for like parameter efficient fine tuning, and TRL, which is for like training a language model with reinforcement learning. And then we'll be having our bits and byte library for like 8-bit optimizer and quantization, and WAN-DB, which is the tool for like experiment tracking and model management. So now we're done with it. So once we done with it, we have to import the necessary Python packages for loading the dataset, model, and tokenizer, and also for fine tuning. So basically, HuggingFace transformer, which is like auto model for casual LLMs, and auto tokenizer, which are for model loading and tokenizing purpose. And then we'll be inputting the PEFT, like which is parameter efficient fine tuning for efficient LoRa based adaptation, and Torch for like PyTorch based model execution, and Hugging Face dataset to load the dataset. I mean, in our case, it's a medical dataset that we will be loading from Hugging Face, and WAN-DB, which is weight and bias for like logging and experiment tracking. And finally, we have a TRL, which is Transformer Reinforcement Learning for SFT, which is for supervised fine tuning training. So let's try the authentication tokens. So once it's done, so now we have to initiate our weight and bias. So this initialize a new WAN-DB run for a project name like Finetuned-Llama 38B on medical dataset, specifying the job type as like training and allowing us to do anonymous logging. Let me go here to the so if you don't have an account in WAN-DB, like try to create it to track your experiments. So from here, yeah, I have already created an account. I have just copied the API key from here to like use it within my fine tuning notebook. So let's initiate it. So let's see the project it have created in weight and bias. So this is a project from where we will be tracking our metrics. So far we haven't done anything, so it's empty right now. And then we have to set the base model and data set, and also the new model variables. So basically we're going to set up the data type and attention implementation in this set. So if you see the torch type, D type, which is torch dot float 16, this line like sets the data type for like PyTorch tensors to 16-bit floating points, which is hop precision. So this can like help reduce the memory usage and potentially speed up the computations, and especially like on GPUs that supports. We'll be having attention implementation here. So we'll be using flash attention if we have the CUDA device available. Otherwise, we'll be go with eager. So this line which like sets the implementation method for attention mechanism to eager. So now we will be like loading the model and tokenizer. So in this cell, like we will load the model from Kaggle, and then however, like due to like memory constraints, we are unable to like load the full model. So therefore, we are loading the model using 4-bit precision here, if you see. So our goal in this project is like reduce the memory usage and speed up the fine tuning process. So you see like by bits and bytes config here. So this sets up the configuration for quantizing the model to like use 4-bit precision, which reduces the memory usage and speeds up the computation. And load in like 4-bit, which is true, which enable the loading the model in 4-bit precision. And then we have our BNP 4-bit quant type, which is NF4, which specifies the quantization type, which is for example NF4, which stands for specific quantization scheme. And again we have our BNP 4-bit computation D type, which is torch D type in our case, which sets the data type for computation. And again BNP 4-bit use double quant, which is true, which enable the double quantization for improved accuracy. And then we will be loading the model here. So auto model for like casual LM from pre-trained, which loads the pre-trained casual language model, and base model is an identifier or like path to the base model, and quantization config you see here, sorry, which is BNP config, which applies the previously defined 4-bit quantization configuration, and device map, which is auto. So it automatically maps the model to available devices like CPU, GPU. And then finally, we are having our attention implementation, which specifies the attention mechanism implementation to use. And let's load the tokenizer and then set up a model and a tokenizer for conversational AI task. By default, it uses the chat.ml template from OpenAI, so which will convert the input text into chat-like format. So here you see the tokenizer, which is auto tokenizer from pre-trained with the base model. This just loads the pre-trained tokenizer using the specified base model, and then the tokenizer is responsible for like converting the text into tokens that the model can understand. So now here, if you see, we are just loading the Lora config. So low rank adaptation, which is used to like fine tune only a subset of layers while keeping the rest frozen. So the parameter we have used so far here are like R, which is equal to 16, which is a rank of the Lora update matrices, and then Lora alpha, which is 32, which is the scaling factor, and then Lora dropout, which is 0.05, which is the dropout to like prevent the overfitting problem. And we will be having our bias param, which is to no bias tuning, and then we'll be having our target modules. So fine tuning the full model will take a lot of time. So to improve the training time, we have attached the adapter layer with a few parameters, making the entire process faster and memory efficient. So if you see here, we have like a model tokenizer, which is coming from setup chat format. So as I have mentioned earlier, we will be using a chat.ml template from OpenAI, which will convert the input text into chat-like format. And then we will be applying Lora to the model from here, like get fifth model. So this function takes the original model and the Lora configurations and returns a new model with Lora applied to the specified layers. So take the original model and apply the pip config that we have defined earlier. And now we have to import the dataset. So to load and pre-process our dataset, we have to load the like a medical chatbot dataset that we have defined earlier with this name, dataset name, and shuffle it and select only the top 1000 rows. So this will significantly reduce the training time. Okay. And then we have to format the chat template to make it conversational. Okay. And then we have to combine the patient questions and doctor responses into your text columns, as you see here. And then we have to display the sample from the text columns. So the text columns has a like chat like format with special tokens. So raw JSON here, which will like create a list of a dictionary representing a conversation between a patient and doctor, and then tokenizer.apply chat template, which will apply the chat template to the raw JSON here without like tokenizing it, and stores the result in raw text. And then we will be applying the formatting function here. So dataset.map, which applies the format chat template here we have defined earlier to each rows in the dataset using 4 parallel processing, so that we are having numpros equal to 4. And then finally we are testing this with accessing the dataset. So we are accessing the formatted text of the 4th sample in the dataset, which is index 3. And then we have to split our dataset into training and validation. So here the dataset is our original dataset, and train test split, which is the method that splits the dataset into 2 parts, training data and testing data. And then test size, which is 0.1, and this specifies the 10% of the dataset should be used for testing, and the remaining 90% will be used for like training. And then next one is like so training the model. So we are like setting the model hyperparameters so that we can run it on Kaggle. So you can learn about like more hyperparameters in the tutorial link that I have provided in the description below. So basically in this tutorial we'll be using all these parameters. So we are like fine-tuning the model for one epoch and logging the matrices using the weight and biases. So you see the training argument class, which helps in configuring the training parameters for the model. So output directory, which just specifies the directory where the training model and other outputs will be saved. And per device trained batch size, which is equal to 1. So it just sets the batch size for training and evaluation to 1 per device. We'll be having gradient accumulation step. It will accumulate the gradient over 2 steps before performing the backward pass, effectively like simulating a larger batch size. And then we'll be having optim, which is paged Adam 32-bit, which chooses the optimizer, in this case a 32-bit version of Adam W. And then number of epochs, which is 1, which sets the number of training epochs to 1. So, and then we'll be having our evaluation strategy, which is steps, and eval steps, which is 0.2, which specifies the evaluation should be done every 0.2 steps. And then we'll be having our logging steps, which is equal to 1, and logging strategy, which is equal to steps, which just logs the training matrices every step. And we'll be having our warm-up steps, which is 10, which sets the number of warm-up steps for learning rate scheduling. And then finally, we have our learning rate, which sets the learning rate to like 0.0002. And then we'll be having our FE16 and BF16, which is false. We are disabling the 16-bit and bfloat 16 precision training. And we have our group by length, which is true, which groups the sequence of similar lengths together to like optimize the training efficiency. And finally, report to VanDB, which specifies the training metrics should be reported to weight and bias for tracking. We now set up supervised fine-tuning, which is FSFT trainer, and provide a train and evaluation data set, and then LoRa configuration, and also training arguments, tokenizer, and models. So we are like keeping the maximum sequence length to 512 here to avoid exceeding GPU memory during the training. So we have mentioned the model, and then train data set, which is data set of train that we have splitted earlier, and evaluation data set, which is coming from the test, and then pept config, which is the one that we have configured earlier for parameter efficient fine tuning, and maximum sequence length is 512, which sets the maximum sequence length for the inputs. And then data set text fields, which is text, indicates the field in the data set that contains the text data in our case. And then tokenizer that we have declared earlier, and then arguments, which is training arguments as well, such as like learning rate, page size that we have defined earlier here. And then packing, which is false, which disables the sequence packing. So this helps in configuring and prepare the SFT trainer for training a model using the specified dataset, tokenizer, and training parameters. So now let's start fine-tuning the process by running the following code. So it's from here, trainer.train. So before training our model, let's try to print the trainable parameters. So here in our case, we have the trainable parameters. So these are the parameters that will be updated during the training. So in our case, these are the LoRa parameters. So the smaller number of parameter is what makes the LoRa efficient. And then we'll be having our all parameters. So this is the total number of parameters in the model. So includes the both frozen, I mean the non-trainable and trainable parameters. So this represents the full TinyLlama model size. And then we will be having our trainable. So which is this shows that only about 0.2% of the total parameters are being trained. So it can be calculated with a trainable parameter divided by like all parameters into 100 like. So this low percentage is a key benefit of our LoRa fine tuning. So here instead of like fine tuning 1.1 billion parameters, we will be only training about like 2.2 million parameters. So this will make the training much more like memory efficient and also significantly faster. are also less prone to like catastrophic for forgetting, and also more suitable for deployment. I mean, the smaller file size for like for the fine-tuned component. Well, this starts the actual training process using the trainable parameters that we saw earlier to adopt the model to our medical data set while like keeping the most of the original model's knowledge intact. Let's wait for the training to finish. So now our training have got finished. So now let's watch out for the weight and bias matrices that we have configured earlier. So basically here we can see the training loss, I mean loss curve, which, which should decrease. And then we have the validation loss, which should also decrease similarly. And there's a gap between like training and validation loss. I mean the smaller gap, which is meant for like better generalization. And then regarding the learning rate, which should shows how the learning rate changes during the training, and it should follow the warm up and decay schedules as well. And then we have like GPU metrics, GPU utilization, memory usage, and temperature. And then finally we have training speed, like samples per second it took for to train the model, and then steps per second as well. And then finally we have our gradient matrices, so like gradient norm. So like we are running this model on like some pretty tight constraints. Right now like we are using the smallest possible batch size, which is one, and only accumulating the gradients over 4 steps. So it's kind of like trying to learn a whole medical textbook by looking at one sentence at a time. So not ideal, right? So just a demo to like showcase how the fine tuning works. Okay, so we are only doing one pass through our data, like one epoch. So think of like speed reading through a medical textbook once. You will just get an idea, like, right? But you will miss a lot of the important details. So in a real setup, you have to go through the data at least 3 to 5 times to really let the model soak in all that medical knowledge. So learning rate here isn't bad, but it's like throwing a model into the deep and without teaching it to swim first, right? So adding a warm up like period would help ease it to into the learning process more smoothly. But what we can do like make it much better is we can bump up the batch size to at least like 4 or 8 if your computational requirement can handle it, and let it train for like 3 plus epochs, and add a proper training, I mean the learning rate schedules with some warm up times, and then throw it some weight decays to keep it from going off the rails, and then check on its progress more often with more evaluation steps, right? So these changes would probably give us the most smoother learning curve and better overall result. So the objective of this tutorial is to showcase how we can fine tune the LLM like LLMA. So what we have to go further is to like to get the perfect result by just doing it iteratively to improve its performance. Okay. So now we have to save the model locally. So this line here you see like it will save the fine-tuned model to our specified directory, and includes like model weights, configuration files, and LoRa adapters, tokenizer files. So this creates a complete like copy of our fine-tuned model for later use. And then when DB finish, it just properly closes the weight and bias logging session. And finally, we have model config catch, which is equal to true, which enable the key value catching for like faster inference and improves the generation speed during the inference, and was likely disabled during training for memory efficient. So it just gives us the run history and run summary. Once done, we have to push the model to the Hugging Face hub and uploads the model. So what it will do is it will upload the model to the Hugging Face hub and making it available for others to use. It's time to like test our fine-tuned medical chatbot. So for the first time, we have like created the input message in the chat format here. So and then it will create a list of like containing a dictionary with the user messages. And then the next line, what it will do is it will apply the chat template to the format message, and once it's done we will be tokenize the formatted prompt, and then we will be generating the response. I mean, here we have put up like our maximum response length is 150, 150 tokens, and it will generate one response. We can generate multiple as well. Like for the moment we'll be generating one response. Okay, and then we will be decoding and clean up the responses, which will convert the token IDs back to the readable text, and then skip special token, which will remove the special tokens like pads, EOS, and split assistant with the index 1, which will extract just the assistant response part. So question is, hello doctor, I have bad acne and how do I get rid of it? So it returns a simple response using our data set. And let's try with another question here. Hello doctor, I do have like migraine and how can I manage it? Again, what it will do is it will create the input message in chat format and apply the chat template to the format the message, and finally it will try to tokenize the formatted prompt. Basically, it will convert the text to like tokens the model can understand, and then creates a tensor, that is matrix of token IDs, and move the tensors to the GPU for like faster processing. And finally, we'll be generating the response with the limit of like 150 tokens, and we'll be generating only one response. And finally, we'll be converting the token IDs back to readable format, and the decoding process, and then we'll be cleaning up the response to print it. So that's it guys, we are at the end of this tutorial, and I really apologize for not showcasing the demo with the Llama 3 8-bit chat model, because in the beginning I was planning to do this tutorial, but I still don't have access to the Llama 8-bit model even after 1 month of my request submission. So that's why we have just showcased the demo on like how we can fine tune TinyLlama on our custom data set. So maybe let's see in the future about the process of like merging the adapter with a base model and converting it to the GGF format and then quantizing it for local use. And I have provided the link to all the resources that we have used in this tutorial in the description below. So that's it guys, we are at the end of our tutorial. So fine-tuning the Llama on a custom data set and using it locally has opened up like many opportunities and possibilities for building innovative applications. So the potential use cases ranges from like private and customized conversational AI solution to like domain-specific chatbots and text classification, language translation, question answering, personalized recommendation system, and also even healthcare and marketing automation applications. So in this tutorial, you learned to like fine-tune the Llama on a medical dataset. I hope you find this tutorial helpful. I have provided the resources that we have used in this tutorial in the description below. See you all in our next session. Until then, this is Abonia. Bye for now. Thanks for watching.